class number 18. Today is 2020 3rd 19. This is the page number 1. So if I pick up from last time, if you remember, we developed the code and I just extend the code from the Q4 to the Q8 and Q9. So the Octave code we have currently can handle all kinds of Q elements from 4, 8, 9. And I just enforce the boundary condition using the row and column elimination. So the code was already uploaded on the Google Drive. All the bugs were fixed. That is ready for you to use. You should try to download it and execute the code, or maybe play with the code, modify it a little bit. Right. But still, we are not done with the code yet, because for the finite element, right now we have displacement solution. Which is already obtained from the equation, which is basically the stiffness times the U and equals to the external force that is applied to the system. So you solve for the U and then the U is going to the xy coordinate. Okay, so xy coordinates along with the U, x plus u x, y plus u y. This is the updated geometry. So something fall. I made the subroutine that plots out the original or undeformed shape and that is the original x and y coordinate, and the deformed shape, which is actually the updated coordinates of x and y over here. Okay, so we can see the deformed configuration of the continuum or of the domain we wish to learn about. But the point is that for the application, for the engineer, well, deformed shape is one thing. You can just make use of it to check if your model is functioning properly. Sometimes you don't make the model that right. Or let's say your model is not correct. Something might go wrong with the boundary condition, something might go wrong with the load, or etc. possibilities that actually could be the reason for the error. Thus, we check into displacement solution that envision you some idea if your model is right or wrong. But for the design point of view, for the application point of view, you might use the deformed shape or the displacement solution just to check the serviceability of your your model, right, of the design. You want one important parameter for your design is the stress and strain. Okay, so the goal for today is that how do we obtain strain and stress from the displacement solution, right? We want to make use of the displacement solution. We want to make use of the system of equation that we rigorously solve, spend a lot of resource solving for this displacement solution. But what do we know more than displacement, right? If you want to design, you want to come up with the size of the member, you want to come up with the configuration or the arrangement of the structure such that you do not overstress. That's the point. Or, well, in the other way around, you do not want to overstrain as well, because this stress and the strain are the function. Stress is actually the function of the strain. So, how do we obtain stress and strain and the stress? So the displacement solution is actually going to give you the information about strain. So for the problem that we are working here, we deal with for 2D planar system, we will get the epsilon x, we will need the epsilon y, we will need gamma x, y. Having these three, you can figure out principal strain. So you can figure out max, principal strain, min. Alright. You can also figure out Mrs. stress, or you can use all of these to check in the failure criteria. Use all of these to check with failure criteria. Right. So the goal is not to overstress. Then it depends on the material you are dealing with. You deal with the metal material, then you check with the Mrs. failure criteria. If you do something with the sort of brittle material or clay, those things you're gonna change the failure criteria to another that is appropriate. If you do the concrete, right, maybe you need to look into something brittle that can handle brittle material like more Coulomb. So that will be the inelasticity point of view. We are not going that far. We cannot afford time in this class. But then, right, so we know that we need to figure out strain from the displacement. So how is it done at this step? How to convert displacement into strain? Well, the idea is simple. When we talk about the algorithm, it will be well, a little longer than what we see in the iPad, but I'm going to show you how to make our code works and be able to compute strain and later on stress if you want. Okay, so as we all know, you have strain displacement relationship. And this is called the B matrix, if you recall. So when we compute the stiffness matrix for the plane element, you have the integration over your domain. You have the B transpose the B, right? You have Jacobian of transformation later, and you have dx, and then you have dy. So inside the B matrix, again, if you recall back in a few lectures, first of all, this is the partial derivative of shape function with respect to x. This is the shape function number 1, 0, 0. Partial derivative of shape function 1 as well with respect to y, and then partial derivative of shape function 1 with y, partial derivative shape function 1 with respect to x. And this structure repeats, so we're gonna see this here, we're gonna see another there. The thing is that we will just need to change the shape function. It doesn't look okay. So we're gonna change the shape function into this, to the corresponding displacement degree of freedom. So this is for number 2, number 3. The detail of how we come up with each of these was already explained, and I'm not going to repeat that. So the cell like this repeats for several times until you get to the end node, right? This move things around a little bit. I ran out of space. So this B matrix, if you multiply it by the displacement u, you will end up with strain. Alright, this is a fundamental we develop. So it is quite easy for us right now. In order to get strain, we just go back to the code we have already. After the analysis, after you perform the matrix inversion of the stiffness matrix K and multiply to the force, externally applied force, you end up with the displacement. You get that set of displacement and back into the process that you used to have for the stiffness matrix calculation. Okay, but you will not compute stiffness matrix anymore for this time. You are going to compute strain, and that will be it. You don't end up with the K. You don't use the K anymore because you just done with it already. Okay, so the procedures here will appear in the next phase when I move from iPad to the computer. So we're gonna see the operation in Octave. Okay, but what we will have so far for now is like this. You have the elements, you have the node. What we come up with will be the strain at the integration point. The thing is that we evaluate the stiffness matrix at the integration points. So when we compute the strain back, the point that makes sense for us to use for the computation, the point means the C and the eta coordinates. So the C and eta coordinates that we have right now, already we established these coordinates for the integration point. When we come back to evaluate the strain, we will use the same set of C and eta for this evaluation. So let's take a look. If we have 9 integration points, actually that means 3 in each direction. 3 integration points in C and 3 integration points in eta. So that makes the 9 integration points. 9 integration points, you have this for each individual element. That sounds scary. Especially when you use a Q8, Q9, you need 9, right? You need to make sure that your evaluation of stiffness matrix is going to be explicit. So you need 9 integration points to ensure the correctness of the polynomial integration. Sorry, when I speak, I cough and I'm in the room which is air conditioned, so that could be the case. And at each point we have quite several components. We are talking about plane problem only. You have epsilon x, you have epsilon y, you have gamma xy. All these trees are available at every single node. So you have number of elements and ELE. How many information that we have? You look into the number of integration points. If we talk about NINT as the number of integration points in each direction, you're going to have NINT squared up. And then what next? At each integration point, you have 3 strain components. I don't know how many elements we have, but this is going to be about 9. That 3, that makes the 27 data already as of now. And these 27 data, you compute stress. The stress could be the nonlinear function of strain. So you're going to have 3 more stress components, right? And multiply by the total number of elements we use in the analysis. So you can see the cost of the calculation that is quite brutal. So you need a good PC. If your PC is not having a large memory, so you might end up with some sort of freezing during the operation. Now, knowing that we will get the data like this. Let's take a look at the data structure a little bit. Okay, this is a visualized data structure I just explained. The data will be stored in three-dimensional array. So first of all, you need the first layer of data to be first index, let's say. So I will call the integration point stress like Tn. Strain at the integration point. So ISTN variable will be named this way. Start from I going to J and then the K. I'm sorry. I means the element. J is the integration point. K is the strain component. Strain component. Oh, this is very disturbing for me. Is it okay to just let me run to my car to get like a fisherman's friend? So it's not going to bother you. Component K equals to 1. That is for epsilon x. K equals to 2 epsilon y or gamma x y. This is element number. Integration point, so that depends, okay, from 1 to NINT square up. Okay, so you get the data structure is going to look pretty much like this. Now, we have integration point strain, but what we need for the next step is the visualization of the strain over your finite element domain. Without the visualization, then it is quite difficult to see the data in as like numbers. Numbers, you're gonna see a bunch of numbers coming out from ISTN here. Too many numbers. So you cannot visualize, you cannot identify where is in trouble, where is good. Okay, so we need the graphical presentation of ISTN. We cannot avoid this part. One good thing in learning finite element is this data visualization. You actually have the background that is coming along with this FEM course, because in order to visualize the stress and strain, we're gonna talk about the functions in MATLAB that we use to explain the magnitude of stress or strain using color. So it is like a color plot. It is the fill function in MATLAB and in Octave. We're gonna play with that. So we take this integration point strain and plot. The thing is that, let me jump to the next page. Okay. Page number 2. When we talk about the stress plot, This is just to remind you about what you used to confront with. Am I a super spreader of COVID? Coughing like this, but it is just during the class time or at the time that I talk too much, then I cough. Okay, here's the thing. If this is the plot between stress versus x coordinate, if we are working on just the simple bar problem, you used to see this already in a homework assignment. I requested you to plot the axial stress distribution of the bar subjected to the load, the distributed load. When you plot, you end up with this picture. Stress is actually varied with the derivative of the shape function. The shape function is used to approximate the displacement, right? Let's say displacement approximation. So the strain and stress will be the derivative of shape function with respect to the domain. That's a thing. In the displacement approximation, we guarantee the continuity over the boundary. No space. Continuity over the boundary is guaranteed. So if we also plot the let me do it this way. Stress in red, displacement in green. Okay. So the displacement is continuous over the boundary between elements, which is this point. If there is another element there, then it will be continuous like this. Whereas the continuity of stress and strain is not actually guaranteed. So you're gonna get the discontinuity at the boundaries. That's gonna make the stress plot turns out to be discontinuous. You will not have a smooth stress, which actually in reality stress must be a smooth function, right? You will not expect stress to be like the ladder step, or over on the left side you have one stress value, on the right side it is another stress value, because you will not satisfy equilibrium of the infinitesimal piece of object. So this is your domain. You discretize your domain like this, and you compute you do the extrapolation, you get the stress distribution. One element may be you zoom into this area. On one side you get 50, on the other side you get 20. So if you take this piece subjected to stress and then you look up for the equilibrium of this little infinitesimal piece, you cannot get the equilibrium equation satisfied. Alright? So that's why I said that actually it is not likely that in reality this stress and strain will be discontinuous. It cannot be that. Due to the equilibrium. So, but the point is that finite element, it is the nature of finite element. We try to just satisfy this continuity requirement for the displacement point of view. So, for the stress and strain, we need to process this data further, and that is the stress or strain smoothing. Stress and strain smoothing. So let's take a look together. You have the domain. I just pick up some point from the domain of our finite element. Okay. Q4, Q8, whatever. If we do the Q4, you have the stress computed or strain computed at the breakpoints. Thus, the information we have right now is just the discrete point data. It is not the data that gives you the field value of your stress or strain distribution in the domain. It is not the plane, right? If you want to express the distribution, you need to construct the plane. So, basically, what we can do is to construct the extrapolation function. Why I said extrapolation? Because we have to extend our knowledge. Actually, our knowledge is inside this block. You agree, right? So, the dots outside the box, you need to extrapolate. If I do like the cross section like this, you know this information here, you know the information there. If I plot the values between 2 points, things inside is the interpolation, but outside your domain still extend to here and there. So you need to extrapolate this part here and this part here. Okay, so basically you can construct the extrapolation function, which is 5. Oh. But once you end up with the extrapolation function, you are going to get the numbers from, for example, this corner is the contribution from the element number 1. Okay, I name the element this way. So over here, let's say if it is 10, you go to the element number 2, you compute the stress at the corner using the extrapolation as well, you get 15. You come to the third one, you get 26. The fourth one, you get 5. Okay, now how do we fix this problem? So there are, well, majorly two approaches. The simplest approach, you just take all these computed stresses or strain from extrapolation and average all of them up. So you take 10, add up with 15, add up with 26, add up with 5, divide by 4. That's it. You get the new number at the nodal point. You get the new stress value at the nodal point. You use this as the representations of the point stress. So you're going to have point stress, point stress, point stress, point stress, point stress, which is the average point stress. And next, you are going to construct the interpolation function of stress. So as you have the corner point stress, right, you construct the plane out of these 4 corner points. So what's gonna happen? The thing is that you will have the continuity over the boundary. So the element boundary like this will be continuous. Stress over the boundary will be continuous. However, this seems to be a very easy one to do, but it is not the best one, in the sense that the operation we carried out by this approach, just averaging the nodal point stress, it is not giving us the the best fit or the most optimal fit to the stress pattern we obtain from the integration points. That is the drawback from just averaging the number. You just do things locally at the point, but the final profile may not may not give the least values of error. So just forget about this. It could be done, but just forget about it. It's not the best thing. So we are going to talk about the least square smoothing. When we talk about stress smoothing, I think of smoothie. Least square smoothing. So we might take a look at the picture over here. Okay, so here I'm drawing the domain. We have nodal points, and we're gonna have integration points. If you do the Q4, you need just again 2 points for each direction. That makes a 4. So we're gonna call stresses at stress or strain, whatever, okay, it is applicable to both, but we're gonna call them like this. It could be sigma x, it could be sigma y, it could be tau xy, it could be epsilon x, epsilon y, and gamma xy. Alright, that could be all of the what I just mentioned, but we're gonna call the parameters. So I will say that sigma star could be sigma x, sigma y, tau x, y, epsilon x, epsilon y, gamma x, y. Okay, so sigma star 2, sigma star 3, and sigma star 4. So we can come up with all of these sigma 1, 2, 3, 4 from stress recovery routine. Sigma stars are from stress or strain or stress recovery routine. It was stored in that ISTN, or if you want to have the ISTS, that is possible. Actually, my suggestion is that if we are talking about elastic, linear elastic, the strain, the stress which comprises the sigma x, sigma y, and tau xy is a linear function of strain. Let me underline a linear function. So, as it is a linear function of strain, then you can keep only just strain, right? You don't really have to store everything, because if you want stress, you just compute it by taking the D matrix and then multiply by strain. And the D matrix is just a simple 3 by 3. You get to figure out the lambda plus 2g, Poisson ratio, elastic modulus. You can get the D matrix very easily. So you take the D matrix, multiply by strain, you get stress. That is okay for the linear elastic problem, because if you store too much information, your computer will be slowed down significantly. Keeps only strain value, so ISTN is necessary. Whereas the counterpart, do not counterpart, actually the linear elastic problem is non-linear. Okay, material. Actually, it is a subset of the non-linear problem. So, the non-linear problem, you have the stress, right, is a non-linear function of strain. Basically, you can determine the such information quite easy. Well, it depends on the material model, of course. If you bump up with the jackpot, you get the headed one. But you can compute stress from strain as well, but as it is the nonlinear function, so you might store ISTN and ISTS. Actually, you should, because at the end of each calculation step, generally for the nonlinear problem, you have iterative solutions, and then you break the data down into steps. Yeah. So for example, I just give you some just rough idea. Yeah, you have something which looks very simple. It could be the concrete, it could be steel, it is discretized, and we are going to push this until it fails. So we apply the pushing force like this. If we run the experiment, we might find that this relationship is found. So the delta and the force which is applied, and the behavior looks like linear at the beginning and then softening and fail completely. So when you run the finite element analysis to compare to model the problem over here, you might just need to break down into several steps, right? At each step, you're gonna have the convergence, you're gonna have convergence, you're gonna have convergence, and so on and so forth. Once you achieve this convergence, you will have the state of the stress and strain that satisfy the equilibrium. So you store all the ISTS and ISTN. So you don't need to come back and recompute the ISTS, because this ISTS could be time consuming. ISTN, this is from the displacement solution, so it does not take so much time, but this ISTS is the nonlinear relationship with the ISTN. But all this, actually the computer software is gonna take care of that for you. So just in case if you really have to how to say, develop your own code, and you might think of storing or the data or information management, you could think of it. One more thing, for those of you who might not do this sort of computer programming a lot before, please do not store this information in RAM. Do not, just write it down to the hard drive. You can pull it up later, fine. But if you stuff it in RAM, your computer will run out of the memory. It goes to virtual memory and etc. You're gonna end up with a nightmare. You don't need to flood your RAM. You want to free it up as much as possible. So stiffness matrix might be in the RAM, but at the end of the step, if you are dealing with nonlinear problem, you should clear out your stiffness matrix, because the next step, stiffness matrix, will be modified by the nonlinearity which is caused in the former steps. For example, if we are talking about this step here, you can see that the slope was changed, right? So the stiffness matrix used to evaluate the displacement in this step will be different from the Ki minus 1. So you don't need to keep this. Once you're done with it, just drop it out from your RAM and then start your new life. Start your new life with the Ki. Once done with Ki, clear it out. So your RAM will be free. Now we come back to this point. So at any point here, you can get stress by evaluate. Don't have space. You can compute your stress using the interpolation function or extrapolation function. So you come up with the just sigma, okay, and then C and eta. I will explain a little bit that sigma at any C and eta point represents the distribution of stress within an element. Using extrapolation. Okay, and this is not continuous. Over the boundaries. Okay, so it can be written in as a function like this. Actually, stress here is a function of C, is a function of eta, and is also a function of sigma star. Sigma star represent the nodal point values, right? Sorry, not nodal point, integration points value is equal to the summation of the interpolation function, extrapolation function, sorry, star I. Extrapolation functions, because we have many, right? And that is the f of C and eta. This is the part for C and eta, this is a part for sigma, so we can write it this way. Okay. Next, as this is not a smoothened stress, okay, it is not continuous over the boundary, so our goal right now is to construct the smooth is to be constructed. How? So we have the unsmoothened stress. We want to construct the smoothened one. We're gonna name it the G. The G, well, as we are talking about the function that describe the field values, you have to include the spacious variables C and eta, of course, right? And this one is going to be using the stress, but stress will not be the stress at the integration point anymore. We want to come up with nodal point stress because this G is the global function. The superscript represents the the superscript represents the nodal, and the N means the nodal point stress or strain. Stress should be stresses. Now strain. And this function is global, so it is established based on global concern. Oh well, it is the function that we came up with to by Kim. Good to know that you watched this one. Very long time no see, Kim. Alright, miss you all. Kim used to be my student back in Texas, Austin. I still remember Kim. Well, that might be the first or the second year that I served as a TA back in UT Austin. So that was around 2007, 2008, somewhere around there, or 2006. I don't remember exactly the year, but I still remember Kim. Okay, so she's doing fine now, I know. Alright. Yeah, very good to see that I have visitors. Yeah. You know, seeing people who might stop by to view this video, this live classroom, is like I'm teaching in the real classroom, but I open the door, and then people just walk past the door of my classroom and just wave hello, and yeah, hello. Okay, so we established the global the G function based on the global concern. We in other words, in the words which is more formal, it is the optimization or minimizing error, because you know that the plane, which is the field distribution using the G in comparison with the sigma, which is constructed based on the element level concern, will not be matched. Okay, so I will say that clearly here. Sigma C eta and sigma star does not match with G function, which is sigma eta and sigma n. Okay, the word does not match implies that you will have error. Alright, you will have error, but how to minimize the error such that the field, the distribution fits with a smooth function. Okay, just, well, too much mathematics words probably, but to make it easy for us to just understand it, you have the profile, you have the distribution of stress or strain given by the sigma, and this will not be the same because the sigma is not continuous and the G is perfectly continuous. Over the boundary, there will not be any misfitting or discontinuity. So knowing that one is not continuous and another is, of course, these two planes will not be just right on the same place at every single location. You understand, right? We need to establish the G plane or the smoothen distribution. We need to establish this such that the error is minimized throughout the domain. So that's why the least square word is coming in. But let me just give just a little bit. Oh, G is the interpolation function. And basically you can use shape function. Because right now, if you want to express any value of stress inside a single element using the nodal point value which are associated with the point on the boundaries, so you are trying to just interpolate. You are not doing any sort of extrapolation anymore, right? Whereas the sigma star is whereas the sigma, just the sigma alone, does the extrapolation because the sigma alone use the sigma star, which is the integration point information, to extrapolate all the way to the boundary of the element. Okay, if you use the interpolation function, the shape function can be used, and it is just the old sets of shape function we used to know. We have the shape function for 4, for Q8, for Q9, then those things will be adopted over here. So basically the error, which will be represented by the E, is coming from, error is from what? From 2, the difference from 2, right? So we have stress sigma as the sigma star function, C eta sigma star function, minus the G function, which is smoothen function. C, you have eta, and you have sigma n. Alright, the difference between these two makes the error. But the point is that to minimize the error, you cannot just do the summation of error, right? The plane, for example, this is one plane, this is another. If you just minimize the summation of error, so this is positive error, this side might give you negative error, so you sum up, you get 0. The other one, you can get 0 error as well, as long as the left side and the right side produce the same magnitude of error. So the error will not be determined by just taking the minimum of the summation of the error over the entire domain, but it will be evaluated in a different way. It will be evaluated by using the key. This is the in Greek, it's called key. Now, since this part here at the top will be element by element in the sense that the sigma was constructed for each individual element, and for the G is going to be using the interpolation function or shape function for individual element. So this operation can be carried out element by element. Due to that fact, the procedures is identical to what we have been doing in the finite the standard finite element procedure. So the summation is going to be there from I equals to 1 to n should be the NELE, right? So operation will be element wise, and then we conduct the integration in your planar in the plane domain. Integration is carried out. What is to be integrated? It has to be the error, but not error alone. It is the error square. If we use the error square, we just take the sign out of the consideration. So the error, the case that I mentioned before, like on one side positive and the other side negative, something like that, we will not be getting any headache from this issue. Okay, so error from this side will be square up, error from the other side will be square up. So you have the positive values of key. And we want to minimize the square of error. And that's why people call it the least square error. We want the least, the minimum scenarios of error square. So the E sorry. Okay, it is better now. C eta, and it is also the function of sigma star, right? From there, and what else? Sigma n. That's all, right? So, so the C eta from both comes in here. This is the spacious coordinates. Sigma star comes in here, sigma n come from there, and we want to integrate over your domain. So your domain right now is in the plane, so you have dx and dy. When you have the square of error, is q square of error how to make use of it? The square of error, you don't know how to equate this, right? You cannot set it up to like the equation. Well, key is this thing, or what is the key? What is it? Do you know the number? You know the value of this? Because we want to, let me ask you, what we want now? We want, our goal right now is to solve for this thing. This is our goal. We want this. But in order to know this, you don't know this. If you don't know on the left hand side, how do you figure out the sigma n? Not possible. Oh, sorry. So if we want the minimum values of E square, you need to, when you want to get the maximum or minimum, the extremum values of the function, you need to take the derivative, right? When the derivative, or in other words, the slope is equal to 0. Zero slope represents the maximum or minimum values. So we take the derivative of t with respect to what? Now let's think about it. What should be this point here? We want to minimize the error. What could we change? What could we set? You cannot do anything with this. It is just your coordinates. You are not going for the point where you get the minimum square error, right? So it is not the derivative with respect to the spacious variables. Is it to the sigma star? Sigma star is given, right? As it is given, you cannot change anything with it. You have integration point stress and strain. Now, how do you change all of them? It is the information which are associated with the displacement solution. So this is another thing that couldn't be used to differentiate. So the only candidate is sigma n, because we can change the nodal point, not integration point. Previously, I'm not sure if I said nodal point at sigma star. If I did, then okay, please adjust your understanding accordingly. Sigma star was supposed to be the integration point. Okay, so we cannot change integration point value, but we still can change the nodal point stress or strain values, because it is something that we want to determine over here. So we take derivative of t with respect to sigma n equals to 0. Okay, so we're gonna get the extreme values of the we're gonna get the sigma later on, sigma n, that give us the minimum least square error. So if we do so, I move this a little bit. Okay, then I do the summation n e l e again, I equals to 1. The integration over the domain still there. You differentiate this term e square, okay, which is a function of this. You're gonna get, differentiate e square, you're gonna get 2e, right, which is the function of this thing c eta sigma star sigma n, and this has to multiply with what? You differentiate e square, you get 2e, and then that's gonna be with the derivative of e with respect to sigma n. Okay, the x dy, and since the g is a function of c eta and sigma n, it is actually can be expanded into node, number of nodes. Well, basically I should call it e tip element type. Talk about Q4, you have 4 shape functions, right? So I equals to I equals to 1, sorry, to E type, right? And that is multiplied by, of course, the shape function has to be there, and the sigma n, okay, has to be there. Basically, this expansion in the summation form could be represented by the shape function times the sigma n, where the shape function has to be like this. You have phi 1, phi 2, phi 3, phi element type, multiplied by sigma n 1, sigma n 2, sigma n E type. Okay, so we have the dot product between these two. Thus, if you take derivative of g with respect to sigma n, actually you have this thing here, right? Derivative of E with respect to sigma n. So E is coming from this. E has the function of sigma, but the function of sigma is C eta and sigma star. It has nothing to do with sigma n. So when you take derivative of E with respect to sigma n, this dies off. Okay, it dies off. How about this? You will have this term because it is the function of sigma n. So the derivative of E with respect to sigma n is equal to minus g sigma n. Okay, which is equal to, now you see that your g is the sigma n times the shape function. So if you differentiate the sigma n times the shape function has nothing to do. It is not a function of sigma n, right? So you differentiate, then this part is gone. What you leave off is only the phi, the shape function. Then you end up with the phi over here. Okay, now what? From this point, we will rewrite this. Okay, so basically, as it is going to be equate to 0, the constant like this, like 2, can be dropped off because it means nothing. If the left side is going to be 0, we can just cancel this out. So we keep only E times the derivative of E. Okay, so let's expand it because inside the E, it has the sigma minus the G. Okay. So 0. I set this. Okay. 0 is going to be equal to summation I equals to 1 to NELE integration. The integration now is going to be change. The domain will be from -1 to 1 because we are going to do the mapping. And we transform into numerical domain. So we have the E, and the E comprises this. So the sigma times this part here, sigma. Okay, so the minus sign has to be out there, and then we have the sigma, which is a function of C, eta, and sigma star times phi, and minus the G times phi. As you change the domain of integration from the xy, so we're gonna have the Jacobian of transformation in there, which is always positive, and then the domain was changed, so you have the dc, the eta. Now the sign, negative sign here, is actually useless because on the left side again it is 0, so you just clear it out. So allow me to just delete it this way. Alright. In a strategic point of view, what do you see right now? 0, okay, means nothing now. One side, sigma here is actually known. Alright, this is a known function. Sigma star is known. Okay, this is a known distribution multiplied by the shape function. Okay, and the other one is the unknown sigma n, right, multiplied by the shape function. Okay, so if you just set these two terms on the opposite sides, this part is like the force vector, pretty much like that. It is the known, it turns out to be the known vector, whereas this one is going to constitute the shape that looks like the stiffness matrix. Okay, so it is the coefficient matrix multiplied by the unknown vector of sigma n, and we need to figure out the sigma n, okay, from this equation. So let's continue. So I'm gonna put the okay, I'm gonna put this, let me just copy to save time. Paste. Okay, just rearrange terms a little bit such that the phi multiplied by the sigma, okay, and Jacobian of transformation dc and d eta. If we conduct the numerical integration, numerical integration is going to evaluate the function values at a point and at an integration point at the time. So what is going to happen here is that you think of the function of, okay, this is the array of phi at wherever evaluated at the integration point 1, 2, 3, 4, okay, multiplied by the sigma evaluated at integration point. Is it going to be difficult to evaluate this part? Not at all, because the sigma is the distribution from the extrapolation function constitute from these integration points values. So if you evaluate the function sigma values at all integration points, then you're gonna get sigma star, right? Turns out to be easy. So you actually do not have to come up with the extrapolation function. You just know that it will be extrapolated, but actually you don't use it at all. Come at this time, you just pick the point values and drop in here. So you're gonna get the vector like data, vector format. And here on the other side, we gonna have the, well, I just going to copy the whole thing. Oops. The point is that I can just delete this part here. Okay, take it there. Right. So let me arrange things a little bit. Transpose. Okay. Okay, so the dimension match properly. Okay, and inside this integral, if you break it down, you find that the g, okay, is actually coming from here. It's a phi times sigma n. So I will repeat this here. I will substitute the g with the phi times sigma n. This two here, actually I should arrange it a little bit to ensure that these two things here okay, phi transpose times phi is going to turn out to be the matrix. Sigma n as it is unknown, I take it outside, it is the unknown to determine. Okay, it is taken outside. Okay, so let me just write it clearly, like to determine. This term the matrix, coefficient matrix. Just think of it like the stiffness matrix. And the left side as it is numerically integrated, if we do it element by element, I think I should keep that. So sigma sorry, not sigma, it is the phi. Alright, phi 1, phi 2, phi 3, and I dot to phi element type. This multiplied by let me put the footnote here. No, not this way. And sigma star. So sigma star is with the I and I. Okay, where the I represents the integration point. So sigma star I can be taken directly from ISTN or ISTS. Okay. So basically I just want to emphasize that there is no calculation. No calculation. You just take it. That's it. This phi. Okay. Evaluated at C and eta at the location of integration points. Okay, so location of integration points I associated with C and eta, I think I can just do it this way. Element looks like this, integration points location. So if you are doing it at this point, the integration at this point, so you evaluate the you evaluate the phi based on the sets of the C and eta of this point, and then you take the sigma star of this point. Okay, you multiply these two together, you have this part here, and this is carried out at a point. So you need to accumulate all of these at first point. You're done with first point, you go to the second point, you get the new sigma star value for the second point, you get the C and eta values for the second point, substituted in order to evaluate phi 1, phi 2, phi until phi element type. Okay, so let me just expand this into the okay, this is page number 3. Oops. No, I got to do, oh, where is it? Where is my note? Okay, alright, just okay, so let me just copy things from here. Copy, and then what time is it? Almost 10. So this term, if we conduct the numerical integration, we are going to clean this out, and we don't have these two. We are going to replace the integration in x in C and eta with the summation. So this is the j equals to 1 and k equals to 1. This is NINT, okay, integration point, number of integration point in each direction. So we have these two summation. Jacobian of transformation, of course, will be evaluated, so we can use just the code we established, we developed it already. Then don't forget that first of all, let's put the index. It is going to be the JK. JK has to be in there, and the weight of integration has to be in there as well, so it has the J and the weight K. Alright, and that is it. So as I told you before, I just want to emphasize for another time that this part here could be sigma x, sigma y, tau xy, epsilon x, epsilon y, gamma xy, or whatever you store at the integration point. You can use all of them to, you can take all of them to smooth out. Right, so you stuff the numbers like this at integration points. Again, ISTN or ISTS in our code is going to be then let's go back and pick this up for this side of the equation. and let me delete up. Okay, so it will be reformed. It will be reformed in the following. This has to be gone. This will be there, and the nature of numerical integration has to be the same, so we copy, and we're gonna have the double summation put there. The thing the CD eta has to be gone. This should be dropped in. The sigma, this part here will be the last thing. Well, it will be determined. You will have the JK, alright, evaluated like this, JK. And weight, right? So I just borrow from here, paste there. Okay, and the part on the left is the matrix. Okay, so you have the vector, pretty much like the force vector, equals to the stiffness matrix multiplied by U. The U is basically replaced by sigma n. The K is actually this one, and the F is actually coming from that one, that side. Okay, so now we are ready to implement the code. So we will not jump to the octave today because we ran out of time already. I was trying to make it possible to switch around between two different platforms, but it is finally not necessary for today. So next class we come back on Monday. We will finish up the code by first of all doing the the stress or strain recovery. So I'm gonna develop the stress strain recovery routine in the class, and after that we will go to the stress strain smoothing. Okay, and we will be pretty much complete for the 2D problems code, because we now can visualize the deformed shape, we can visualize the stress and strain. So we meet the requirement for the finite element. Once you have all this information, you can make use of the data of the results from the finite element analysis. Okay, so let me wrap up for this class. This video will be uploaded on YouTube later on. It might be today evening or it might be tomorrow, but it is there on Facebook automatically. Alright, okay, so we're gonna see you again on Monday. Thank you for watching.